Welcome everybody, and thank you for attending our presentation on our long fiber materials. So this is what we'll be covering today. I'm going to start the presentation by talking about in general what long fiber materials are, composites are. We'll start by defining long fiber materials. We'll talk about the performance benefits. We'll specifically talk about long glass and carbon fiber reinforcements, and then some of the other specialty technologies. Then I'll hand the presentation over to Mark Henry, and he'll talk about designing for long fiber composites, some of the strategies, tips, and performance analysis. And then we'll finish up with a Q&A section. So let's begin by defining thermoplastic composites. They use melt-processable thermoplastic polymer matrices. They can be reformed and recycled. Common processing methods are injection molding. They can also be used in compression molding as well as profile extrusion. So let's talk a little bit more about the benefits of, fiber reinforced plastics. So they can expand plastics performance envelope. They're a cost-effective method to increase mechanical properties of lower cost thermoplastic polymers. Reinforcements can be incorporated into any thermoplastic polymer, anything from a commodity up through an engineering type resins. And there are different reinforcement options. There are particulate fillers, which add to stiffness but don't add to strength or other mechanical properties. There are short chop fiber materials or reinforcement options as well. And then what we're going to be talking about mainly today is long fiber. These offer the best structural performance, obtainable with injection molded compatible materials. And then there are also continuous fiber fabric mesh prepregs, and these are used in layup process. They have limited geometries that can be used, and they have long cycle times, adding to the cost of manufacturing. So here are some of the common filler types. You can start down at the bottom. We'll talk about from a cost standpoint and then temperature limitations. You have natural and synthetic reinforcements, and then we move up through glass, basalt, ceramic, up through some of the metallic reinforcements as well. Those are higher cost, and they offer other benefits. Carbon and metal obviously are conductive, and they're electrically active. For the most part, we're going to be talking about glass and carbon today. So here's some of the uniqueness of long fiber materials. They're made with the pultrusion process, which in the upcoming slides I'll show you the process of how they're made. Fiber reinforcement is unidirectional and continuous through the feedstock pellet. So essentially the pellet length equals the fiber length. Pellets are typically cut to 12 millimeters. This is for mechanical performance. It optimizes mechanical property performance, but also makes it easier to handle and process in the injection molding process. Typically after you mold the thermoplastic composites, the mean fiber length in the parts will be anywhere from 3 to 6 millimeters. And this is going to give us the optimal mechanical properties into the parts. High fiber aspect ratio results in more robust performance. So these are different than short fiber compounds, which are typically chopped fiber and plastic melt blended in compounding extruder. They have random orientation, and the typical average fiber length is less than a millimeter. So this is our process for making thermoplastic, our pultrusion process. And you'll see over on the left, essentially what you'll see is we have fiber rovings, and those rovings are pulled through an impregnation die where they're wetted out. We surround those materials with plastic, and then we pull to the right, and those are basically we're producing strands, and then those strands are chopped, typically to 12 millimeters. So you get continuous strands of fiber melt impregnated through the polymer die. and you get better fiber and polymer bonding, which equals to higher performance and mechanical properties, as well as cosmetics, because you don't get any loose fiber in the materials. Typically, we'll make composites based on 20 to 60% fiber contents by weight. And that depends on which type of fiber we're using, and as well as the thermoplastic base resin. So what are some of the benefits of long fiber thermoplastics? Stiffness and modulus. This is a function of fiber rigidity and content percentage. So if we're using carbon fiber, it's going to be stiffer and stronger than glass, just as an example. Also, design characteristics, which Mark Henry will go over later in the presentation, also can be used to incorporate and improve stiffness. And then we have extended thermal capabilities, such as HDT, with our fiber reinforced materials. Secondly, strength and load carrying. Fiber content percentage provides stepped approach to increasing strength. So as we increase fiber percentage, we'll see stiffer and stronger stiffness and strength go up in these materials. And then we can also look at fiber alignment perpendicular to stress forces and component design characteristics to contribute higher composite performance. And then toughness and impact resistance. This is where long fiber materials really earn their stripes. We get higher impact properties than any other reinforcement in plastics versus things like short fiber. So we get the impact properties along with the stiffness and strength. Fiber networks pick up stress energy and distribute over a wider area, and we'll take a look at that in a following slide. And then we also have resistance to permanent deformation and crack propagation. So this is a graphical representation of what I just spoke to. You can see along the bottom we have fiber length, shorter fibers to the left and then longer as you go out to the right. And then you have performance level on the left-hand side of on the graph. And you can see as you go out in fiber length, you'll start to see increases in strength along that blue line as you get over 1 millimeter. And then also, but on the red line is where we really see the performance benefit. So once you get over 1 millimeter in length and increasing, now you'll see your impact properties and toughness go up. So this is a molded part over on the left. Basically probably a long glass nylon 50%. And then the part on the right is where we burned off the actual resin. And what's left is the glass reinforcement. And this shows you why we get the mechanical properties that we do in long fiber composites. Essentially, you have this skeletal fibernetric matrices that you can actually, what it does is it actually distributes the loads and gives you better properties, including impact. A couple of other things to look at is you'll look at the center portion of that part with those thin ribs, and you can see that there's actually fiber in those areas as well, and there's good length to it. So our materials can be molded into thinner wall geometries and still maintain mechanical properties in those areas. And then if you look at the bosses around the surrounding area of the part, you can see that those are very thick sections. And what happens with that fiber in those areas is we get very low shrink. So now you can actually mold thicker sections without sinks or voids and things of that nature. And then the overall is that now you can break some of the design rules for injection molded part because you can vary wall thicknesses, both thin and thick, a little bit more with long fiber materials. So that's an added benefit. We can also look at mass reduction and lightweighting. Our materials are perfect for that. Things that have to be carried, that have to be portable. So now we can decrease the weight of those and increase energy efficiency and reduce user fatigue. They have high strength to weight ratios to displace traditional materials like metals, and more robust material equals less use and thinner walls. Also, you see very good dimensional stability with long fiber materials. You get things like better creep resistance or load over time, We can consistently hold tolerances. You've got low coefficient of thermal expansion, and you typically get uniform and predictable shrink. They're less prone to warp, and you can minimize sink in heavy wall sections. One of the other biggest benefits of long fiber materials is fatigue endurance. The graph over on the top right shows this, where we've done some fatigue testing, and you can see on the bottom is a 50% short glass nylon, where you get about a 10,000 or 11,000 fatigue cycling. When you switch over to our long fiber materials, it's 20 times higher. So very good fatigue resistance. You also get vibration and sound dampening, and they're reprocessable and recyclable. So for metal substitution, you look at long fiber composites. They're the go-to material for metal replacement. They have high strength-to-weight ratios, and as we talked about, the ease of forming and manufacturing specific to the injection molding process. And what we find is that metals are often over-engineered, an often over-engineered material solution, chosen just because they're familiar, the company's familiar with that or in those applications, rather than some of the practicality. You need to look at beyond cost per pound or kg of material. You have to look at a systems cost when you're looking at composite materials. Injection molding plastics are a cost-effective method to produce components in high volume and repeatability. Low cycle times equals high output. And you can obtain net shapes to finish levels specs in a single step process versus some of the other processes used in metals. And then you can also eliminate secondary operations and finishing steps by using. Plastics injection molding provide more design freedom than metals do. You can achieve more complex geometries, intricate details, only machined once into a mold tool or a mold versus metals that have to be duplicated endless times at and with no additional cost. You have complex 3D geometries, provide opportunities for part consolidation, and Mark Henry will hit on that a little bit later in the presentation as well. You eliminate fabrication of multiple pieces and related assembly steps. You have greater design flexibility, which allows integration of elements that improve functionality and provide product differentiation. You get corrosion resistance to thermoplastic composites, and they can be electrical and thermally isolation for those as well, and in some cases radiolucent for medical applications. So in order to convert from metals to plastic composites, here's some of the things you have to think about and look at. It requires a complete understanding of the application usage conditions, operating environment, environmental conditions, etc. You know, your typical and maximum loadings, length of time that they're under load, operating temperatures, and then the chemical and radiation environment as well. The economic benefits from conversion, target costs for finished components, things of that nature. And the ability to optimize design for new materials. Plastics are rarely successful as a drop-in substitute for using a direct metal design. So we typically will have to adjust the design to allow our materials to be used. And then you use computer simulation tools to predict reinforcement plastics behavior and design feasibility. So let's talk about a couple of specific materials, and we'll start off by long glass fiber composites. So long glass fiber has been used in polypropylene for a long time in semi-structural automotive components. 30+ year track record for metal substitution. Glass is a strong but flexible fiber. You can combine it with any commodity or engineering thermoplastic polymer to boost mechanical properties. It's a very economical reinforcement option. It boosts the strength to a higher level than short fiber materials or other reinforcement options. You get the added toughness benefit retained at low and elevated temperatures. So with our glass reinforced long fiber materials, you will see the same impact values at -40 as you do at room temperature. You extend the heat deflection temperature significantly beyond base resins by using long fiber materials, and then they're also colorable for product branding or ID. So this is a graphical representation of some of the things we were just talking about. And essentially, if you look at the green spider graph, that's a 50%, at the blue, you see a 50% long glass fiber PA66. And you'll see we have higher flex modulus, strength, and tensile than short fiber material, which is represented with a green line. And then we also get the added benefit of that notched diazide impact, or toughness in impact resistance. And here's some values both for polypropylene long glass as well as nylon 6,6. And you can see some of the increases in percentage that you get for the different mechanical properties. And if we go over to the right and look at nylon 6,6, you can see huge increases in tensile strength, tensile mod, flex strength, and flex mod, as well as impact properties, and heat deflection temperature or heat resistance. And this is showing the impact properties as well as strength versus long glass versus short glass. And you can see across the board at every loading percentage or reinforcement level, long glass outperforms short glass materials and adds to the strength of just the base resin as well. And then along the bottom, you can see a comparison of our long fiber materials, some of those grades versus metals with regards to notched diazide impact. And we actually have higher impact values than magnesium and aluminum. Here are some general applications that our materials are used in, things like fasteners, medical fixation clamps, outdoor sporting goods, including propellers. And these are some of the typical applications. They're also used in automotive applications as well. So let's switch gears and talk a little bit about long carbon fiber. So carbon fiber is widely adopted in aerospace and defense and sports and rec markets. And it's increasingly being looked at in transportation markets to reduce weight and improve fuel economy. It's got a high-tech perception with consumers. Its products incorporating carbon fiber composites have a marketing advantage in that way. There can be a cost to entry barrier because of the cost of carbon fiber. So that's one thing that has to be looked at, and that's why you have to look at a systems cost versus just a cost per pound or cost per kg. They are electrically active and are conductive, and they're only available in black colors. And you can see the lower density of carbon fiber versus glass. Carbon fiber is synonymous with high performance, the pinnacle of performance in injection molding plastics. It's the top choice for lightweighting. It's 30% lighter than glass fiber and 50% lighter than aluminum. A good target area for us is aluminum, because our properties match quite well, and you get the added benefit of the reduced weight. And here's some, down along the bottom, you see some of the mechanical properties that we get with carbon fiber versus glass. And you can see at lower loadings, let's look at the blue graph, 30% long carbon fiber versus long glass. You can see we actually have higher strength, and obviously lower density comes along with that. So if you're really looking at lightweighting and stiffness and strength, carbon fiber is the way to go. And here's some performance data comparing both a polypropylene and a nylon 6,6. And you look at the, if you look over at the right again, like we did the previous slide, at the delta or percentage increase, you see that in the PA66 we have a slight increase, 15% approximately in density, but the mechanical properties go up significantly, both in tensile, flex mod, and then impact as well. So you get that high performance level with the carbon fiber is added at a lower density. And here's some other data. We're just comparing short carbon fiber versus long carbon fiber, similar to what we did with the previous slide with glass. And you can see the increases that we see in stiffness and strength as well as impact. And then along the bottom, we compare some long carbon fiber materials versus metals. And you can see that specific strength we match very nicely with some of the metals properties. And here's some of the applications that long carbon fiber is used in. Again, outdoor sports and rec, lightweight archery bow risers, bicycle components, and as we noted earlier, that it's used a lot in aerospace for seat components and other areas as well. Not only can we add reinforcements like glass and carbon to our long fiber materials, but we can also tailor them specific to your application by changing base resin. They can be used in any base resin from a commodity polypropylene or olefin up through engineering resins like nylon, TPUs, all the way up to very high performance resins like PEEK. Beyond glass and carbon, we also have basalt and aramid and stainless steel fibers that we use as well. And then we can add multifunctional performance with regards to lubricants. If you need high wear resistance, we can add PTFE and silicone, flame retardants, as well as color. And color would be specific to glass reinforced products. And one other material that I'd like to highlight, because we talked about carbon fiber being one of the barriers of entry is cost. We came out with a new material, which is our hybrid material, where we can actually put glass and carbon fiber in the same pellet. This will bridge the gap between using either one of these fiber types. So now we can balance out performance level, the stiffness and strength that you get with carbon fiber, and impact that you get with glass, as well as the cost. Hybrids are a lower cost option than carbon fiber, and it's a single pellet solution. And we can tailor the material to the performance requirements needed. So we can vary the percentage, total percentage of the reinforcement level, and then we can vary the performance of the glass and carbon to, again, tailor it to the application requirements. And here's just a spider diagram and some information comparing what the properties do, the change in properties that you get from a hybrid material versus a glass and carbon. And you can see that if you do a 40% reinforced nylon 6/6, 20 long glass and 20 long carbon, your impact resistance goes down slightly versus an all glass reinforced product, but it definitely goes up about 125% of that of a carbon reinforced material, or 25%, excuse me. The strength goes up significantly versus glass fiber, and you only lose a little bit of strength versus an all carbon fiber matrices. And then you also increase the stiffness significantly over glass, and again, it's fairly close to the carbon fiber. So a 50% reduction in carbon fiber content reduces material cost approximately 40%. So this is a good option if you're balancing out both mechanical performance as well as cost versus a carbon fiber reinforced material. Another grade that I'd like to highlight is our maximum toughness grade. This is ultra durable long fiber reinforced nylon composites for demanding applications like sporting goods. You can see a 40% increase, as much as a 40% increase in impact resistance versus our standard long fiber materials, and a 400% increase in toughness over short fiber materials. And this can be added to both the long glass and carbon product lines. And here's some data just comparing long glass MT materials at the top, as well as carbon fiber at the bottom. And you can see, if you look over at the right, that you see significant increases with our MT products versus short fiber, as well as our standard long fiber materials. And another product that offers some benefits is called our Velocity product. This is easily where you can easily mold high fiber content materials, up to 50 or 60% in nylon composites. And what you can see with these materials is that you can see significant increases in flow length, as much as 30%. We can also cut injection pressures in the realm of 40% and reduce cycle times as well. and then you get enhanced surface appearance. So if you look at the two pictures, our standard material is on the top, and then the velocity product is the picture on the bottom, and these were molded at the same molding conditions, and that you can see that we get a lot better surface of finish with the velocity material. And then another material that I'd like to highlight is our Reinforced TPU. This is a translucent material, and believe it or not, that dog bone on the right is actually molded with 45% glass, long glass material, and you still have contact clarity. So this is a translucent material that can be used in applications where you need rigidity and strength. You know, things that you might be looking at is internal, where you need to reveal internal components, you know, things like monitoring windows and LED backlighting. So again, we have the ability with our materials to tailor our materials to the application, whether it's wear resistance, electrical, flame retardant, appearance. We have a lot of tools in our possession to actually tailor the material to your application. So in summary, long fiber materials are great for metal substitution in the areas where you have lower performance, where other plastics are failing, specifically in impact and strength. They can carry loads, they have added toughness, and of course they're great for weight reduction. You also get the design and functional enhancements with being able to go to injection molding versus metals, and they're simple, relatively simple to manufacture. So that's the materials review portion, and now I'd like to hand it over to Mark Henry Wakeham to talk about our design, the design portion of our presentation today. Thank you.
Thanks, Steve. I like to, every time I'm talking or explaining how to deal with long fiber, especially if it's to somebody who's used to dealing with metals or maybe unreinforced plastics or thermoplastics, there's an object or an image that I like to explain first. So this way, keep this image in your mind when you're thinking about anytime you're going to switch a material. So this triangle kind of depicts each of the characteristics that you want to keep in mind, such as the production method. In this case, it would be injection molding, but it can also be extruded or compression molded as well. The reason it's important to keep that in mind is you want to think about what path the material is taking in a cavity in the case of injection molding, and how flow is going to be emitting from the source, in this case a sprue. And you want to think about how that flow is traveling through the cavity, how it's taking shape, what the fiber orientations are as they're flowing, but also the process itself. When you're dealing with injection molding, there's going to be process settings, there's going to be injection speeds. All of these things need to be optimized. And then you want to think about the material itself, like the long fiber. Which type of fiber do you want to deal with? Glass, carbon? Do you need long fiber? Does the part need to be fiber reinforced at all? What kind of resin matrix will this be working with? And you want to think about the part geometry itself and the tool design. Is the part geometry moldable? Is it compatible with injection molding? If not, how can you do so? If you're going to have, let's say, undercuts, how do you achieve those in a cheaper way to get those geometries? So once again, anytime you switch between materials, you want to understand the material itself and how it's manufactured into a geometry. And that's how you'll get to the best outcome. Other things you'll want to consider are the amount of fiber loading, and typically it ranges between 30 and 50% by weight, but sometimes it's okay to just use 20% if you don't need a lot of structure out of the fiber. Again, you want to think about the forming process. Are you injection molding, extruding? Is there going to be maybe a machining post-op afterwards to get a geometry? And the earlier you think about that, the better. You'll also want to think about fiber chemistry. Is it carbon? Is it glass? Maybe it's a hybrid. Now, what resin might be going with this fiber? Which ties us into the fiber morphology. And that's, what is the chemical reaction happening at the top of the top surface of the fiber? How is it bonding with that resin matrix? Now, typically this is done by what's called sizing, and this is a chemical coating on the top surface that helps that bonding method. And then the next thing you want to think about is the fiber orientation. when it comes to structure or a higher stress area in the product, you want to think, am I orienting the fibers properly to the loading condition? Similarly to a rope, you don't want to push on a rope, you want to pull on a rope. So your loading condition and your fiber orientation go hand in hand. You also want to think about your fiber length or the aspect ratio. Once again, do you need long fiber? Is this going to be impacted? Is it going to see a fatigue life? If so, these are things that are going to steer you towards long fiber. And also another thing I like to imagine when I'm dealing with long fiber is kind of like rebar and cement. Short rebar wouldn't hold much cement together, but long rebar does. Here are a few products that highlight different aspects of the strengths or even weaknesses of the material itself. On the top left, you have a crossbow riser that's subjected to loadings of about 1,800 pounds of stored energy. That's a lot of loading, and a lot of people think, wait, a thermoplastic can't handle that load. Well, they'd be wrong in this case. It is also half the weight of its aluminum predecessor, and that gave a huge edge to that market. On the image on the bottom left, you see a geometry that's a lot more intricate. You see ribbing, things that if you, let's say, were machining metal, that'd be too costly to make that geometry. But when it comes to injection molding, you can make that intricate geometry all in one shot, within a minute or 2 minutes, and you only need to get that geometry into the mold once, and then you can make it millions of times more. And that's all about thinking about getting material where you need it and optimizing on your design and not just thickening a geometry. So you have to think about all these new design freedoms that you get out of molding. And on the right, we see this, it's actually a cell phone bracket that's used to hold the frame inside of a cell phone. Now, carbon fiber was selected here to replace magnesium just because of the lightweight behavior and how much easier it was to produce, and the EMI shielding that it produced, because carbon fiber is electrically conductive. So that supplies a whole nother intrinsic value to the carbon fiber that most people don't realize. When you're looking at replacing a metal part and you want to go to a fiber reinforced part, here are some of the perks that you can get out of that. One is that you're retaining geometric dimensional stability under loading. Another, that's just a fancy way of saying it's a stiff material. It would rather, especially when we're dealing with high loadings of carbon fiber, it would rather break than bend. So that would be more of its yielding behavior. But if you tailor down or taper down the amount of fiber loading, or you're going to a glass fiber, it's going to have more flex in it. So it would rather flex than break. So these are things that you can tune based on the fiber loading that you place into the part. The other obvious perk is the low weight to high strength ratio. As I said, it's about 50% lighter than aluminum, and it's about 18% lighter than magnesium, which is a popular weight-losing material to put into a product. And once again, that molded in geometric intricacy. So if you wanted to put fillets or stress concentration reducing geometry in there, you don't have to feel guilty. In a past life, I was a mechanical engineer who used metals. And every time you put a fillet or a stress reducing geometry in there, you felt guilty. You know that the cost of the material or of the product was going to skyrocket. But now you have that design freedom. As a designer, I really appreciate that, being able to throw in a fillet where you want, or maybe a more organic looking design to increase just the aesthetics of the product overall. And you have injection molding, and the huge perk is obviously the really short cycle times compared to machining out a part or even casting a part. And then the assembly part consolidation, we'll dive into that a little bit more. And that conductivity manipulation, if you're dealing with carbon fiber, depending on the amount of loading you're using, you're manipulating the electrical conductivity of the part. And that has really useful ramifications when it comes to the EMI market and trying to electrically shield your product from whatever EMI waves are coming in from the surrounding electrical products. So that's a good one to keep in mind as well. And then low thermal conductivity. We see this all the time when it comes to metal replacement. If the object is going to be, let's say, touched by a human in a cold environment, you don't want that metal absorbing all of your heat and hurting your hand from feeling that quick thermal energy loss. So it's a lot more comfortable to hold in the cold. And you have that molded in color control. So if you want something to look aesthetically one way or another, you have that option, as long as you're staying in the glass fiber realm. Carbon fiber tends to be black or shades of gray along the way. And you have that corrosion resistance. Obviously, you're avoiding rust or maybe other just corrosive behaviors that happen while you're getting surface-to-surface contact with other materials. One thing that I really like dealing with designing with a fiber-reinforced resin is that it's actually machinable. Similar to aluminum or steel or any of that, you can actually go in with a CNC and post-op a geometry if you want a certain accuracy, or if you wanted to put threading into the part directly, known as direct tapping for the threads. So here's a chart on the right that talks about 50% loaded glass and 40% loaded carbon fiber, and these were just plaques that had threading tapped directly into that material. And you can see some impressive strengths. I was actually even surprised at the pull-out strengths after you put, let's say, a 1/4-20 bolt into a 50% loaded glass fiber brick. We were able to get strengths of 2,440 pounds. That's impressive. I don't think most people would think that would be the case. And then moving on to 40% carbon fiber with a 1/4-20 bolt, you see 3,116 pounds of pull-out strength. That impressed me. I don't know about everyone else. And if you know you're going to be disassembling or reassembling very often and you're worried about cross-threading, maybe you want to look into having inserts placed. And you can do that by sonic welding inserts in, or you can insert mold them by just putting the inserts into the mold and having the flow wrap around those inserts. And along those same lines, you can insert mold a lot of geometries. If you have a wear surface that you're concerned about, the image on the right depicts a metal slip ring, and that's just to reduce any concerns about surface wear as let's say an axis or an axle is getting twisted and torqued repeatedly in the same position. Now, to the part consolidation, I think this slide really depicts it in an easy to understand way. Every red dot depicts another component that was consolidated. So on the image on the far left bottom, you see 4 components that were consolidated and they were molded as one part instantly, having a cycle time of 1 to 2 minutes. That's a huge perk. You don't have to have somebody assembling all those components using adhesives, and you can just skip the whole middleman of somebody assembling those components. And as you can see with the other 3 components, they have 3, 4, and 2 different components that were consolidated in one shot. Now that's very powerful because you're obviously reducing labor, which means you're reducing cost. You're reducing the time that it took. You're reducing the amount of shipping that you had to send things from different countries, from different states, and just everywhere down the chain that's beneficial. People ask me often, what thicknesses do you recommend on this part? Now that's a much tougher question than it sounds. In traditional resins, you obviously want to stay pretty thin, and I'm talking in the range of 100th of an inch. But now, depending on the amount of fiber, the type of resin, the flow length, all of those attributes to the design influence how thin the part can be. So if you're using a low fiber loaded glass, for instance, with a short flow length, you can get 60th of an inch. If you're dealing with, let's say, a high loading of carbon fiber in a viscous resin base or matrix, you're going to start needing it to be thicker. That recommendation would be the ideal wall thickness, about 1/8 of an inch thick. If you have a very long flow length where it's over a foot, let's say, you're going to start needing to up that thickness just so that you don't have a lot of shear on those fibers as they have that long path flowing through that channel. Now, you can see at the upper end of that scale we have 1/2 an inch. Now, I don't really recommend using 1/2 an inch thickness, but the amazing thing is that you can actually get away with molding a part that thick. Now, it's important to realize that you're going to actually get diminishing return on the strength of the material itself the thicker you get. The reason for that is that you're not getting the same orientation as the part gets very thick. And when I say very thick, I'm talking over a 1/2 inch thick. So keep that diminishing return of strength in mind. But let's say you have organic reasons or ergonomic reasons, such as holding a handle. Maybe you need some thickness there just to make it a little more ergonomic. Feel free to do that, but realize it won't be quite as strong. I also get the question often, what safety factor do I need to avoid creep? When you're dealing with metals all the time, the concept of creep can be a scary one. So the typical rule of thumb here is to use a 2-time safety factor to avoid creep. If you know you're going to be dealing with a lot of environmental changes, like very high temperatures or very low temperatures or high moisture conditions, maybe a lot of UV exposure, I would even suggest using a 3-time safety factor to avoid any creep concerns. Now, the image on the bottom depicts a mesh for an FEA. So while you're running an FEA, also keep in mind that you want proper fiber orientation at the places that the FEA is saying that you're getting high stresses. A good way to imagine that is, let's say you know the part's going to fail, and you know where, let's say, a crack would initiate, which direction a crack would travel in. You want to make sure that you're going to be getting perpendicular fiber orientation to that crack propagation. I know it's a little bit tricky to understand. I hope that made sense. But once again, it's going to be very part related, and you can always call us and ask about that, and that's not an issue. So when I get the question, how do you manipulate fiber orientation, which is the obvious next question, you can do so by gating location, part geometry, wall thickness. You know, a lot of people who design for plastics are familiar with the term race tracking. People who deal with metals haven't heard of that before. Race tracking is the behavior where a flow actually travels faster through a thicker conduit. Similar to water going through a pipe. If it's a thicker pipe, you can get more flow through it. So you can actually use wall thicknesses to start manipulating the speed of the flow. Now, if you do this improperly, it can backfire, but when you know what you're doing, you can actually harness it to get the fiber orientation where you want and how you want, or at least at the places that you're most concerned. So back to part thickness and fiber orientation and strength. This is a part that I learned a lot from early on, about 4 years ago, and this was a connector rod. Originally, the connector rod had a very thick section. When I say very thick, I mean it was about 3/4 of an inch thick. Now, the challenge here was that it took a long time to cool off. When we're talking about a molding cycle, because of that thickness, it takes longer to cool. And you also have a lot more internal stresses happening. We can also see what that's doing to the fiber orientation at the core of this part. So now what I did here, I was curious to see what the fiber orientation was like on the inside. So I actually kind of cut a notch into the top of this part. And then I impacted it from above to just create a fracture so I can look internally at the fibers. Here I've also overlaid some colored dots so that you can see what I depict as excellent fiber orientation, decent orientation, or poor fiber orientation. Poor fiber orientation being in red, and excellent being in green. We can see that the best fiber orientations are closer to the surface of the part. The closer you get to the center of the part, you get more poor fiber orientation. And the thicker the part is, the more volume that's getting poor fiber orientation through the cross-section. So one thing that we saw to strengthen the part was that we can actually reduce the wall thickness of this part, making it thicker. So you can see that on the image on the right. You see we've cored the part, which is really adding ribs in this case. So the overall part thickness, or the nominal wall thickness, is about 400 thou of an inch. And that's still pretty thick when it comes to a plastic molded part, but you're seeing much more fiber orientation depicted by more green dots through the cross-section. Now this was beneficial in several ways. The part was lighter, it needed less material, so it was cheaper, and the cycle times were faster, and we had less internal stresses. And the part was overall stronger. So that's very contrary to how somebody might think if they're used to the metals industry, where they just want to make the part thicker if it's, let's say, overstressed. That's not the case. Actually, there is a diminishing return once again if you get too thick, and it actually becomes weaker. I like this image because it actually depicts fiber flowing through a geometry. Now this image was achieved by first having a virgin resin that was in a barrel and then purging in the carbon fiber filled resin. And so this way we can actually see that 7 micron thick fiber traveling through a part. I think that's very interesting. This image is pretty familiar. You heard Steve talking about it earlier. I just wanted to get into some other details or just expound on what he was saying. On the left, we have a zoom in of what that fiber interface is looking at. And it's just all of those fibers are kind of meshing together, almost like a spider web. And that's how we get that excellent energy dissipation during an impact, because those fibers are long enough to bring that energy to the surrounding or several surrounding fibers so that they can kind of work together to absorb and dissipate that energy. Immediately under that, we have that black and white just image of holding it under a microscope and looking at a break interface. You can see that long aspect of the fibers, so aspect ratio of those long fibers as they are broken and having to pull out of the other side of the part, or the break interface. Now, the longer these fibers are into the opposite side of the break interface, the more energy it takes to cause the break. And this is another reason you want to make sure you're getting that fiber orientation perpendicular to that break alignment. Hopefully that makes sense. Now, to reiterate what Steve was saying about these bosses, once again, as a designer, you have this freedom to make a more robust boss, and that kind of carries over to all kinds of geometries. You don't have to worry about sync nearly as much. It still exists, but it's not nearly as much of a problem. So you can have all those robust, stress-reducing geometries like the fillets around it and all of those curves. And back to that center geometry where you see that kind of that mesh behavior, it's still filling that very thin wall. So you're still getting the fiber orientation, or just fiber in general, in that location. Many times people ask me if you're getting any fiber there, and this is proof of it. Okay, since I have to speed things up, so I'm going to run through some of these slides. I want to remind everybody that as you're looking at the strength of your part, or you're running an FEA on it, you want to remember that the data sheets, or the strengths on those data sheets, are depicted from information collected from an ASTM tensile bar. Remember, you get a lot of alignment in these bars. So if you have a thick geometry, you don't expect the strength to correlate exactly with what the tensile bar was doing. So keep that in mind as you're designing. Here's a good example to remind everybody that you shouldn't just swap out a material or hope that the material is going to be strong enough to do everything you need. You want to look at your freedoms now that you're injection molding and think, can I add any more geometry to really bank on what the material is capable of? So on the left, we have a tray that's about 14 inches long, 4 inches wide, without ribs. And on the right, we have the same tray with very thin ribs there. So take a look at the two materials we used, which was a 40% loaded glass fiber nylon with ribs and without ribs. So with the glass one, it weighed about 10.1 ounces. And when a crush load was applied to it, it withstood 985 pounds. When the ribs were added, this weight only went up by about 10%, and then it was able to carry 10,252 pounds. So for 10% added weight, you got about 10% strength as long as 10 times as much strength, as long as you're applying materials in a useful location. When you compare it to the carbon fiber, it started out at 9.2 ounces, able to withstand 2,055 pounds of crush force. Adding those ribs, once again, added about 10% of the weight, but it was able to carry 14,691 pounds. So always keep in mind the freedoms you have for adding design geometry. Another thing to keep in mind is don't use really narrow gates. Traditional gates are about 1.5 by 1.5 millimeters. You're going to want to use larger gates just because you don't want to shear the long fiber as it's entering the part, or you won't benefit from the long fiber aspect of it, and you'll just be getting a lot of short fiber in the part. With that in mind, remember your sprue and runner system. You want these to have smooth, rounded edges so that the flow isn't hitting any shear along the way, so you're retaining as much fiber length as you can. People ask me if you can do auto degating on the part. You can, but remember, since they are long fibers, if you auto degate, the runner is going to pull fiber out of that interface, so make sure it's not on a cosmetic surface. Once again, there's a lot of simulations that we do to compare and take a look at, one being injection simulation, fiber orientation simulations, warpage simulations, finite element analysis for the stress side, and for the deflection side. So as we look at all of these together, we can start looking at what is optimal for the geometry. So with that being said, how clients typically deal with us to get information or to learn more about what is optimal or moldable for their geometry is that they send us the geometry that they have. And then we have discussions, maybe we'll attend in person or have even a video conference. And then we can pull up that geometry on our CAD softwares. We can run FEA or you can run FEA. We can run mold flows, or you can, and simultaneously, by looking at mold flows and FEAs, we can identify stress loading locations, and we can identify poor fiber orientations or weld line areas. And by looking at the two, we can start deciding where do we want to gate, where can we manipulate the weld line locations to be, or maybe eliminate them altogether, or where do we need to get the fiber orientation we need to withstand the stresses that we're seeing. So it's an iterative process where we're going back and forth between those two simulations. And that's a very powerful strategy. And then it's worth a discussion. If you need any assistance, we don't mind helping, and we're very good at communicating these things. So to summarize, we like to help you up front with the concept and work with you on a formulation that is optimized for your needs, and then look at it analytically using software to identify what will optimize the geometry or your product. And then we'll look at the best production options. All right, thank you. That concludes my presentation, or our presentation, and now is a good time for question and answer. Thanks.